So we'll talk about the SLS, the Space Launch System, which is just a launch vehicle, a rocket. We'll talk about Artemis, and we'll talk about some of the technology that. So here is just a picture of the South Pole of the moon saying, hey, we're going to the moon, and basically is to learn how to live in other worlds, right? So rather than going straight to Mars, like with humans, we figured, how about if we start a little bit closer to home and kind of wring out any issues with the systems that we would be implementing in the moon. So that's the reason, that's one of the reasons why I tried to develop a moon base first before sending astronauts to Mars. In addition, what is it that we will do on the moon? You know, many things, as you could see there: gain confidence in human robotic exploration, operate the systems on the surface from lunar orbit. And lunar orbit is a little bit different from Earth orbit, and there's some challenges to that. Conduct science experiments, look for minerals, right? Prospect for any resources, return those to Earth, do power technology demonstration like fission, operate autonomously from another world, establish logistics, really get to live in that environment, right? So the moon has no atmosphere, right? So it's never been weathered. No water, I mean, no flowing water and no atmosphere, right? No air, no wind. So all the material is kind of jagged. That plus the fact that it gets pelted by micrometeoroids all the time. So it's actually electrostatically charged. So dust mitigation is a big deal on the surface of the moon. But why, let me ask you guys, get you a little bit more engaged. Why the South Pole? Why do you think we're going to the South Pole in addition? What is it?
Is it closer? Is it closer to Earth?
That's a good answer, but not the one I'm looking for. What else?
Is it more like Mars?
Okay. Anything else?
There's something there that you're looking for, like a resource.
Exactly. What am I drinking? What am I drinking?
Agua.
Water.
What's water made out of?
Hydrogen and oxygen.
Right. And what's fuel made out of? At least the fuel that we use for the rockets.
Hydrogen.
Hydrogen.
And oxygen. Both.
So you want to make
Liquid
fuel
oxygen. Exactly. There you go. So rather than bringing fuel from Earth, we could harvest it on this. Yeah. Exactly.
to make the trips longer.
So
exactly.
I was going to ask this question. So to put it in perspective, how much further is Mars from the Earth than the moon?
That is a great question, and I got a slide that will answer that, and we'll show you. Give me a couple of more slides, and I'll show you that slide.
Because when you look at the diagram, it's like, oh, it's only 2 inches away, but
yeah, let's take a look. All right, so this is just, hey, we left, but we will coming back, right? That's Apollo 17. So the vision is different this time around, and basically is that we're gonna go to stay. So you guys who are just in high school, right? Maybe working, living in the moon when you get to be a little bit older. So the space economy is booming, and I'll talk more about that. So the name of the program is called Artemis. So if you've had any type of Greek mythology, yeah, whatever, education, you will remember that Apollo, which was the first name of the program that we named to go to the moon, had a sister, and a sister was called Artemis. So hence the name of Artemis. And Artemis when we actually land humans back into the surface of the moon, onto the South Pole, it'll be both the first female and the first person of color will be touching boots on the South Pole of the moon.
That's
Okay.
cool.
Yeah, very cool. So we'll talk about deep space exploration. We'll talk about a little bit about this stuff. We'll talk about a space station that we're calling Gateway that'll be around the surface of the moon,
So
around the orbit of the moon.
speaking
Talk
about of the colony on space, given that like NASA is the one spearheading this project, what country would have claim to the moon?
So no one has claim to the moon. That was done a long time on the Moon Accords.
Yes.
So, yep. So nobody has.
After we landed on the moon, it was a whole thing with the Soviet, Soviet Union and all that. But if we start putting our citizens on the moon, basically, like, would that change anything or no?
So space law is a huge field. I'm an engineer. I'm not a lawyer, but the moon belongs to all inhabitants of the earth. We did not, by putting our flag on the surface of the moon, we did not claim the moon as ours. That was very specifically done. The moon is not US. We went, we landed. I mean, Indians just landed on the South Pole as well with a robot, right? A lander. So
yeah, but human beings. How many people have touched down on the moon?
How many? That's a question I was going to ask you next. How many missions and how many people?
2 missions?
Nope. Tell you what, you could Google it, but the answer of how many people actually walked on the surface of the moon is 6. So, but Google that and make sure that you understand why.
Just 1 Apollo. Oh?
Yeah. How many Apollo missions? So this is a simulation of Shackleton crater, and this is the so it gets shadowed, it gets sun. There are areas in the South Pole of the moon that are permanently shadowed, hence there's more water. So we're interested in trying to see, go into those lava tubes and see what what are the contents of the minerals right in there. So that's one of the areas that we're planning on landing. So somebody asked, how far is Mars? So let's talk about return. So it's always good. So on the ISS, right, if we were to depart the ISS on a vehicle, on a Soyuz or a Proton vehicle, or even a SpaceX Dragon, it takes about 3 hours, right? You got to go, re-entry is about 3,000 degrees. You're going about 17,500 miles per hour, and the distance is about 250 miles, right? So probably about the distance from where you're at to where I'm at. So imagine that distance from like Miami to where I live, and you put it vertically. That's how far the ISS is relative to Earth. That is low Earth orbit. Okay. The moon takes about 3 days to come in, right? So a little bit farther is about a quarter of a million miles away. You'll definitely come in a lot faster and a lot hotter, right? But then look at Mars. Look at the difference in Mars. That's huge, right? That's a lot.
And that's why I kind of asked that question, because the whole Mars, life on Mars and all that, you have to be able to sustain 9 months in a fuselage vehicle, in the fuselage of any transport vehicle, just to get to Mars. And the Earth and Mars isn't clocked, always together. So it might be on the best day, correct me if I'm wrong. On the best day, it might be 9 months, but if you launch at unopportune time, it takes you a year.
So we wouldn't, right? So we're able to use orbital mechanics to figure out when is it that we would definitely need to go.
Yeah.
And it you know, and going, it all depends how the planets are aligned, right? They're closer certain times of the year, and not just years, but you know, every 2 years Mars is closer than it's not. So it depends when it is that you're going. So anyways, it basically just giving you a heads up that imagine not testing your systems, going to Mars, and then finding out, oh shoot, I had an issue, which I could have fixed, you know, if I were to know this about in the moon. And hence, that's why we're focusing on trying to develop the systems to sustain and operate reliably on the surface of the moon first before going to Mars, right? And that's, by the way, and that distance is relative. It's relative to the engine propulsion systems that we have today, right? Imagine if we had a hyperdrive. That would not be that big of a deal then, right? You guys are Star Wars fans, maybe Star Trek. So, right, engage and you go, you know, but we don't have that. We got basically, you know, solid or liquid propellant. We got testing ion engines. Yep, but that's still not as fast as, you know, light speed.
So
yeah,
go
ahead.
back in space and the whole zero gravity. Like, if you can explain that again, there's no friction on space. There's no air friction. There's vacuum, right?
It's a vacuum. Yeah.
So like, can you I heard a story a long time ago that if you get a if you can potentially go into space and you get a fire extinguisher and you press the fire extinguisher, that little amount of compressed air that is in the fire extinguisher will blow you around for miles and miles and miles because there's no surface, there's no friction, there's no air friction, there's no air resistance, there's nothing.
Yeah.
It's vacuum.
Yep, that's true.
That's true.
Wow.
Yeah. It's a vacuum. There's no air. So any reaction, there's no opposite, you know, in a 1G, which we live in, you know, Newton's, what's the second law or third? Every reaction has an equal but opposite. In space, that's different.
It's opposite, but it's multiple. Like,
so orbital mechanics is a cool, if you guys thinking about orbital mechanics, is a great field in science that you could study. Those guys, and we have many of them here that study orbits and figure out which are the best orbits to fly into. So, yeah. So anyways, go ahead.
Sorry, I know. Back to the vacuum thing. When you go out on a spacewalk, like, it's just so, like, if you saw the new SpaceX suits, I don't know how close NASA and SpaceX are, in terms of, but like, you see those SpaceX suits, like the old astronaut suits, when you go on a spacewalk, were these big bulky things that were hard to move in, and now SpaceX came out with a newer suit that was easier to walk, like, you know, easier, more agility. Explain to me how, when you go out into the vacuum, you don't just like implode. You know, we're not humans. As humans, we're not made to be in such high of a vacuum. Is that the right term?
So, have you ever dived before?
Yes.
Okay. So how far deep have you gone? How far?
100 feet.
100 feet. All right. So imagine going 1,000 feet, right? What would you need? You can't use the same wetsuit that you have on. You would have to use a pressurized pressure suit, right? It's no different. It's no different. Vacuum and deep water has very a lot of commonalities. So the same, the concept of a pressurized suit for deep underwater missions is the same concept that we use for in space, EVAs or, walking outside the space station. It's a pressurized suit. And so there's different types of suits for different things. We have our own for EVA, for external vehicle activities, because it also has the capability to attach to many different places. It has a kind of like your tank, your reservoir system, so you can breathe for a long time. And it has lights. It's got different things, and they have worked for us, and we've tested them, and and those suits were a lot different from the ones that we flew in Apollo. So as technology improves, so will suits, right? So on this chart, just giving you, preparations like in orbit, some of the things that we will learn from operating in orbit or deep space, and those things that we will operate on the surface, right? And those things that we would hope to learn will kind of get us more ready for a Mars mission. So if there's anything that I'm trying to push for you guys to understand, is going to the moon helps us understand a lot of things that we have yet to figure out, right? Radiation happens to be one of the big ones, right? There's this things called GCRs, or galactic cosmic rays, that basically comes in and damages your DNA, and it's not good for you. So we're trying to figure that out, how to prevent GCRs to making a havoc out of your bodies, specifically for long duration things. And maybe, who knows, somebody in that room is going to be studying radiation effects, and maybe in the future you'll get to help us figure that out. But I'm telling you, we're going to need a lot of help. It's really, we've only begun to scratch the surface, right? If you think about, I'm going on a tangent here, but let's just kind of get things in perspective. So what's the name of the, so we're in a solar system, right? How many planets?
8.
8.
8. All right. Okay, you guys, Pluto's out. I get it. What's the name of our galaxy?
Milky Way.
Milky Way.
Milky Way. How many solar systems, give or take, are in our Milky Way galaxy? Give or take.
300.
It's in the millions, if not billions. Numbers of solar systems in our galaxy. How many galaxies? Billions.
10
Billions.
billion.
Just billions of galaxies.
And so how much space is there in space?
So, to finish my thoughts, we have only put a human in our moon. That's the equivalent of open up house, your door, open up your front door, and stick your big fat thumb over the cross threshold of your door. We haven't gone too far. So it's a huge space, right? We only have gone to the moon. And so yeah, there's a lot of opportunities for a lot of things. So if you're thinking about space, it's really cool. Get a little video. Hopefully you heard that one.
Yeah, we were able to hear it.
Okay, good. All right. Thanks for that. All right. So we'll talk about the rocket, a little bit on the Orion, which is the capsule. And so think about this vehicle, this new vehicle, as it's got a lot of different configurations. So we could actually send different things, right? In regards to the shuttle, let's see. So if this is the shuttle, you see how these solid rocket boosters, this one a little bit taller. That's because this one has one more segment than this one's had. Same diameter, same thing, same everything. It just happens that this one has one more. Okay. So it's got a aft cone section. It's got a forward section for the cone. These would come back and we will retrieve them. This does not. These two things, this solid rocket boosters, which are, they're basically solid propellant. It's got the same consistency of your pencil eraser. It's called the composition is ammonium perchlorate.
It's
And
not like a rubber substance, right?
it's like a rubber, yeah, and it needs a lot of ignition to actually get it burning. This tank was basically two tanks in one, had liquid oxygen and liquid hydrogen. Same thing here, liquid oxygen, liquid hydrogen, right? Then there's adapters, and then the interstage to be able to take the Orion to the lunar orbit, and this is a launch abort system. So the difference is just capability, you know, adding more adapters so you could actually send longer things. And this is just in comparison with Apollo Saturn V. And if you've ever been to New York, this is about, you know, it's about that high. There's a lot of words here, but basically it's got a lot of capability, right? And we have different configurations that we could use to send different things. So we're using the same similar boosters as we use for the shuttle. They provide 75% of the whole thrust, you know, thrust of the engines. We use the same engines for the shuttle. These are called RS-25. So the shuttle used 3. We're having 4 here. So we call this the core stage, right? The first stage. And then it's got different adapters that we put up. And this is a little bit of simulation of the first flight of the Artemis. If you guys ever, not sure if you guys got to see it, but, you know, launched it from Cape Canaveral here, went around the moon, and then we actually went as far as we could, which is the farthest that we've ever been to, and then give another loop and then came back and landed in the Pacific. So that was Artemis 1, right? Uncrewed, no astronauts. Artemis 2 will have astronauts. And by the way, this is just this was just older pictures. And the reason why I like to show these is because this is where we had small satellites or CubeSats are on these orbital stage adapter, and these things will be these things will jettison once they were closer to the lunar orbit, right? They will just kind of be jettisoned out. And this is our ICPS. This is where it's got an engine here, and the Orion goes on top, and basically is the one that takes it to that orbit. And this is a video of us stacking the boosters. So the boosters come in sections. They all come all the way from actually it's Northrop Grumman now, but they come in rails, and then we stack them up. So this is just putting the last cone on. These 2 boosters are attached to a platform by 4 bolts each. So I want you to think about that. So this is attached to the bottom with 4 bolts, and this one's attached to the bottom with 4 bolts, right? Just keep that in mind. Look at these guys in the inside, in the middle, right? They're just doing a stress test. They're just pulling or pushing on that booster to make sure the tension on those bolts are good. Right, so this is just, and all of this is being done inside our vehicle assembly building. If you've ever been to Kennedy and seen the vehicle assembly building, that's the inside of it. So this is different stages And then this is where we actually test our engines. So the engines themselves, not the boosters, are tested in Stennis Flight Center. And we'll give you a rundown of what that sounds like.
Go for engine start.
H-buoys are on and engine starts has been okay. Engine starting up now.
Personnel, please continue to monitor your system, and grass is in control.
So that was a test of using, just go back real quick to it. I mean, that was a test of using the first time the liquid oxygen, liquid hydrogen tanks, the first time that we tested the engines, we gimbaled them. So those were all tested, and those were the same engines that actually flew. So this is a little simulation of how that first stage then arrived at Kennedy. We shipped it on a barge, and we basically take it out of the barge and take it to our vehicle assembly building for subsequent lift. It goes from horizontal to vertical, and then it's lifted up and across the transfer aisle so that it could then be mated up to those two solid rocket boosters. Okay. And so this is where it's going to be coming to, right? So remember, this too has what you call it, 4 bolts on each end, and there's adapters to these things and up here as well, and that's where that first stage is going to come into. So here's a video of it being, brought up vertically and moved up and across a transfer aisle. So this is a long day, right? Over in the vehicle assembly building. Make sure that everything is done very slowly, but no errors. We have these huge cranes on the top of the roof, and they're able to lift that first stage. And it's empty now, by the way. The 2 tanks inside, they're empty. This is fueled at the pad when right before launch. So imagine it's like your gas, is a car without any gas in it right now. So then we take it across that transfer aisle and we very gently lower it down and attach it to those points on the solid rocket boosters. So that whole orange looking tank, which is 2 tanks in one, it's attached to the white solids. Okay. The orbiter used to be similar, where the orange tank was attached to the SRBs, then the actual orbiter of the vehicle was attached to the orange tank. In this case, we're not attaching anything else to the first stage. Okay.
So
Do you have any questions?
Yeah, with all these new companies like private companies like SpaceX, Blue Origin, is NASA seeing that they're kind of becoming like the low man in terms of technology and whatnot?
So we have if it wasn't for us, SpaceX really wouldn't be doing what they're doing. So we have a contract with them. They supply, right? So we're actually trying to help the economy by getting U.S. companies to kind of step up to the plate, and SpaceX has done a great job. So every time that most of the time when you see a commercial resupply launch going to the ISS, that's because we're paying them to do so, right? We bought that service for us. So they think about it as a UPS, right? So they're the truck, and we give them
The
food, we give them, yeah, the package, and they take the package up to the ISS, which is great for us because that's what we needed. All right. So that's just more pictures of the business and the 8.8 million pounds of truss. This is the launch vehicle stage adapter being placed on top of the first stage. And that adapter just connects to the different sections of the rocket. And then this is the inner stage. Here's that engine. It's an RL-10B engine that has about 24,000 pounds of truss, and that provides a transfer lunar injection burn for Orion. That basically says it helps to get into that lunar orbit. And these were older pictures because these were pictures of the small sats that were integrated on that orbital space adapter for Artemis 1. We're not planning on having anything on Artemis 2. And these are kind of older type pictures, you know, simulation. And then Artemis 2, there's a lot of progress happening for Artemis 2. This is you know, the Orion capsule. It's going to take has the capability for taking 4 astronauts. And it'll be manned, but they're not going to land on the surface of the moon, right? They're just going to go and test the human systems that were not really integrated on the first Artemis launch, right? Those are currently being done. So these are some of the progress that have been, you know, continue to work towards Artemis 2. We're hoping it will go next November. We'll see, maybe a little bit later than that. And then Artemis 3 is that first time we get humans back on the surface of the moon. So this is going to be, you know, either a woman or a person of color. They're going to be the first one putting foot or boots on the ground. Okay. And there's a lot of activities, testing the solid rocket motors, doing a hot fire. All the engines are complete, at least the RL-10 engines. So there's a lot of activities that are happening towards Artemis 3 already and beyond. Okay. So how are we going to land? How is it that we're going to actually land? So this was just the vehicle to get them there, right? But Orion does not have the capability to land on the moon. So how's that going to be done? Anyone?
How's it going
Yes,
to
no.
land?
Yeah, how are they going to land on the surface of the moon? Say that again?
Are they gonna do it manually?
Oh, a good question. I mean, what kind of system? So we're trying to get humans on the surface of the moon, but not through using the actual Orion, but we actually have put out contracts, and those 2 contracts have been led. One of them is going to be SpaceX, and the other one's going to be Blue, right?
Blue.
So, yeah, good. So they are both developing landing systems. Okay. So the rocket we did, the capsule is done, right? We go into orbit. How do we land them? So SpaceX is going to have a system. You've probably seen it. It's this huge thing right here, right? So we've done a contract with them. They're going to develop this kind of landing system. It has a crazy way about it. Is they're sending up a booster or think about this storage depot as a gas station, and then they'll be sending tankers to fill up the gas station, and then they'll send the Starship on top of a booster, and basically that booster will be refueled on orbit and then land on the surface of the moon. So it's very you know, Buck Rogers type of stuff, but it's kind of cool. So here's, you know, detailing here's the gas station, and then a bunch of tankers. It gets filled with propellant. They go into the orbit, Orion. The astronauts go from the Orion capsule to the Starship, and then from the Starship they land, and then they come back up, and then the crew returns. So it's a crazy operation, crazy cool. I mean, that's what I meant. They've also done a lot of things with the elevator, cargo elevators that go to and from. As you probably heard, Starship did have a test that didn't go as well, but they're working on it. So that's good. Over in Boca Chica, and we have a manifest for all the things that we're planning on sending. So, and this thing gets updated, so you could see Artemis 2 in 2024, then Artemis 3, and then a whole lot of different commercial landers as well that provide capability, and so on. So it's you guys whose career are just, kind of getting going. You should think about how can you become part of this as well. And this is not just NASA, but commercial industry as well. I mean, here, and I'm only about 2.5 hours away from you. Blue Origin has got big old, facilities, SpaceX, companies like OneWeb, ULA, Northrop, Rocket Lab. There's all cool companies to work for, and if I were you, I would look to them, not just NASA, to get an internship or work, with. So it's a great type of time to be a young person looking into a space career. And this is just a simulation of some of the landing areas that we'll have, that we're looking into. Another little cool video.
At NASA, we have always answered the innate call to go.
With Artemis,
we are going to stay.
proving that humanity
can live on the moon,
Mars,
and other worlds,
and share the wonders of the solar system with all.
Our story is one of people.
all those who make this journey possible.
From advocates across communities,
to companies across industries,
to countries around the world,
we achieve
this collective endeavor.
Our efforts create impact for all.
Technologies that revolutionize industries.
And jobs that bring prosperity to people.
The discoveries from space
benefit the way we live on Earth today.
And those from the moon
will create a better future
for generations to come.
But to do that,
we must go.
Hi, I'm Chell Ingram.
My name is Raja Chari.
Kayla Barron.
Kate Rubens.
Hi, I'm Christina Cook.
NASA astronaut Joe Acaba.
Jessica Meir.
Woody Hoberg.
Ann McClain.
Stephanie Wilson.
My name is Johnny Kim.
Nicole Mann.
Victor Glover.
Jessica Watkins.
Hi, I'm Matthew Dominic.
Jasmine Mogbelli.
Frank Rubio.
Scott Tingle.
This is what we will do.
Let's go.
We go to the moon to learn how to live on other planets.
For the benefit of all.
Question.
Is that cool? All right.
Yeah, Mr. I have a question.
Yeah.
So like most of this presentation or you've been showing us has been pointing to the fact that the whole end goal is to reach Mars, right? We go to the moon to reach Mars and just make it easier. So what exactly is the end goal for NASA or just private companies in general in reaching Mars? What would it benefit to human society or just the world in general?
Well, that which you're probably holding in your hand, your phone, came out of space technology. That perhaps has some benefit to your life already. So all the infrastructure of telecommunications, satellites, GPS, X-rays, that all came from spending research on space, and we believe so, as we're constantly, proving that any research associated with getting us into space will only benefit us here. And I'll give you an example, because the ISS, right? So the astronauts that go to the ISS, they're doing experiments there 24/7, and they're trying to help live, improve our lives in terms of medicines, different technologies, increase crop production, and so on. So going to Mars, who knows what other new technologies we'll figure out or find out as we go there. Communications. We're trying to develop a GPS and communication system around the surface of the moon, around the lunar orbit, that would allow us to do a lot better communication than we have now, which is there's a 3-minute delay between communications to and from. Science, growing crops in space, understanding the different things that happen with the lack of with the lack of gravity. Telemedicine, helping people from one place and another. All of that has come from space research. So yeah, there's a lot of resource. It has been said that the amount of resources that are in space, you just cannot calculate, right? Because of the vastness. Now, the challenge is how to capture those resources and make them useful.
Okay.
Right? Plus, you have in your DNA the need to explore, the need to do things differently, right? So
yeah, we do.
Yeah, there's a Russian scientist that says Earth is the cradle of mankind, but we're not supposed to be in the cradle forever. Something like that.
Supposed to go out.
Hey, I just wanna, if you guys have any final questions, like to wrap it up, because we're about to, school day is about to end. I don't want to cut you short, but really can't.
I'm good. Actually, I'm gonna stop.
Any final questions?
I'm gonna stop sharing, and you could ask me any questions that you want.
Were the people in the last video you showed us gonna be in the mission?
Those are actually true astronauts that were in the last video. So you'll be seeing those names come up. Yeah, come up. Some of them will be now launching in Artemis 2, right? And some of them have gone already to the ISS through the SpaceX Dragon capsule. So yeah, and who knows, maybe there's some one of you there who may be applying to be an astronaut eventually, and you get to go. So so I was just like you, by the way. I went to high school in Miami, went to Miami-Dade, North Campus, and then I went to University of Florida. So I wasn't that much different from the guy who's picking his nose right now. Just kidding. I was just kidding. So my point being that I was not any different from you. So from your background, from where your guys are at, not very much different. I just kept going and kept doing things. So if you have any interest in a career in space, and it doesn't have to be working in space, but you could be working to support the development of space activities, then go for it.
Awesome. Thank you, Dr. Nunez. Really appreciate your time. If you don't mind, we're going to get a picture. We got you up here on the, I'm going to turn the thing so you can see it. We got you up here on the Promethean board right there. So I'm going to have the, around it, and then just, you'll be there, and then we'll get a picture. I guess that way. While they're doing that, here's the picture.
Cool. All right.
Those are airplane seats that you're looking at. MD-83 airplane seats.
Oh, wow.
Yeah. Over here you got Yeah, you see, here's one of our simulators. There's another one right there.
Oh, wow,
So
cool.
guys, line up like next, like on either side of him, so you can see him. We want to be able to see him too. All right. And then you see you got space references here, just so you can see. Well, it's kind of stuff to see.
Yeah, very cool. Hey guys, you guys should be, you know, not just proud, but you know, not everybody. I did not have those labs when I was in your shoes, so I didn't have none of that.
All right.
So
All right. So yeah, just look at your camera. So that way it looks like there we go. Perfect. All right. Ready, guys? 1, 2, 3. Perfect. Thank you, guys. All right. Thank you, Dr. Nunez. No more on the clock, guys.
all right, guys. Good luck to you guys. Study hard. Get A's.
All right. Thanks. We'll do it again another time. Appreciate it.
You bet. All right.
Take care.
Bye.